Excellent. Okay. So we're going to build up to something called the ideal gas law equation, which actually links the state of all four of these variables of a gas. But before we do that, we're going to kind of take pairs of these parameters, gas parameters, and a lot of times this is very intuitive. I'm introducing something, it's not an equal sign, it looks like an infinity with a byte taken out of it. So like infinity, you guys would probably do this, it's very pretty, right? And if you take a byte out of right here, you have a proportionality symbol. Okay, so proportionality symbol. So we say pressure is proportional to temperature. So if things are directly proportional, as one goes up, the other goes up. Okay? So you probably know this. I usually think of temperature. If I increase the temperature of a gas, the pressure is going to increase. It's kind of usually the direction I go with it. Now, as I take pairs of these things, I'm assuming the other two things are staying constant. So in this relationship, I'm assuming what? The volume and number of moles are constant. Okay, so they're directly proportional. And here's my video. I'm getting close to being able to show my videos. If you take Gen Chem 2, I think I'm going to be able to project my videos. It's something about QuickTime, and it's like a kind of a buggy sort of thing. So anyway, what this would show you, this video would show you, is that it kind of shows the little gas particles bouncing on their side of their container, and you kind of hear ping, 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 and then you jack up the temperature and you hear ping, 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 ping. Okay, so you increase the pressure as you increase the temperature. Okay, so proportional. Pressure is proportional to number of moles. And I brought in some things to kind of show you, but I think a good example of that is if you inflate a balloon, okay, so this is just like a little balloon inflator. Okay, if I inflate a balloon to basically its capacity, okay. Okay, so let's just say that's about as big as it can get, okay? If I keep increasing my number of moles of gas particles, okay, I'm going to increase the pressure here. How can you tell? Well, I can have a pressure gauge here, or I can just kind of feel that it's more taut. Okay, so they're proportional. And this one has kind of got the similar dink, 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 dink going along. And then the first one, it's got some balls in there, and the next, those are gas particles. The next one, you put more gas particles, and ding, 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 ding. So increase and increase peak. Makes sense? So now here we have an inverse relationship. So to show an inverse relationship, we can use the proportionality symbol, but we show that volume is proportional to the inverse, or 1 over pressure. So now here finally we have something, as volume goes up, pressure goes down, okay? As volume, here's one way to look at it, as volume goes down, pressure goes up. And let's see if I can show you this one. I won't. Go find that little yellow one coming up, or orange one coming up. Okay, so I'm going to go ahead and hopefully, these are water balloons, so they're not meant to do this. But I'm just amazed at the circus people who can make little animals out of them, little clowns. Okay. So there's a certain pressure in here, okay? It's got a certain volume. What if I decrease the volume? What happens to the pressure? Decrease volume, increase pressure. You can't tell it, but if I pass this around, I'm literally decreasing the volume. And those little gas particles, N is the same. I'm assuming T is the same, even though my hands are kind of warm. Okay, temperature is the same, but the pressure increases. In fact, it can increase to the point of compromising the rubber. I should have warned everybody. Sorry. Okay. So decrease the volume, increase the pressure. And how do we show that? We show that proportional to the inverse of the other. Okay. So yeah. In order to ultimately get at what we say, I kind of think of as the state of a gas, we need to say what the pressure of the gas particles are, what volume is containing those particles, what the temperature they're hanging out at, and what's the number of moles that are in that particular volume. Okay. So we said that pressure is proportional to temperature. That means one goes up, the other goes up. We said that moles and pressure are also proportional. And then we said that volume and pressure are inversely proportional. We can show that by proportional relative to the inverse of the other. Okay. So now we get to these three gentlemen's laws. I kind of smirk because women have done wonderful things in science. Men have done wonderful things in science. These all happen to be of the latter gender. So Boyle's law looks at two things. Okay, the two things Boyle's law looks at is volume and pressure. And we already said that volume and pressure were inversely proportional. So we could say volume is proportional to 1 over pressure. Charles has to do with temperature and volume. Volume and temperature are directly proportional, so volume is proportional to temperature. And then Avogadro, not so surprising, has to do with N. Okay, so Avogadro looked at the number of moles. And he said that the number of moles is directly proportional to volume. And this actually, this makes sense. If we go back to the balloon, kind of as it's not inflated at all, in the process of inflating it, I'm going from 0, n is equal to 0, to now n is equal to some moles, okay, some more moles, and the volume should increase. Okay, so the volume increases. So in General Chemistry 2, we kind of build on a lot of things we learned in General Chemistry 1. One is gases. Now, we're going to come up with the ideal gas law equation. I'll go ahead and put it up here because a lot of you have already run into it before. The ideal gas law equation relates these four variables, and it says PV is equal to nRT. We're kind of building that to that this morning. This afternoon? Oops. Okay. So PV equals nRT. R is the ideal gas law constant. So for you geeks who like to think of the multi-universe theory of this is only one universe and there are other universes kind of in bubbles, 52. That 52 of them? Okay.
DC Comics.
In DC Comics. Now, I was being serious. There actually is a number associated with R, the value of R, ideal gas law constant. And I like to think that if you're in another universe, it would be a different constant. And it's quite possible. But in order for gases to follow the ideal gas law equation, okay, they need to be behaving ideally. And a gas is behaving ideally if basically all of those particles are independent of one another, kind of as I've drawn them up here. Each one, if I were to number these gas particles, they don't care that the other one's there. They're independent. They're not connected. Their collisions don't affect each other, which is, and actually, them being independent of each other is pretty good if you are at low pressures. So the lower the pressure, the more likely that is to be true. Okay. So this is at low pressures. Okay, low pressures. The other thing is, if they have a lot of kinetic energy, as kind of being shown by this arrow, the more the kinetic energy, the more likely they are to be kind of oblivious to each other. So they're at low pressures and high temperatures. T is high. So ideal behavior generally is at low pressures and high temperatures. The other one is that actually we know all matter has mass and occupies space. So even though those gas particles occupy a space, we're going to say that that space is negligible relative to what they're bouncing around in. So that space is 0. Is that fair? Well, again, the larger the container is relative to their volume, the more likely that is to be true. So again, that's true at low pressures. So this is the two assumptions, and at the Wednesday probably we'll talk about, well, what if that's not true? Actually, we basically take that equation and kind of modify it a little bit for non-ideal gas behavior. Okay. So Boyle's, we said, related volume and pressure. And we said that they, as one goes up, the other goes down. And I'm going to introduce something that's a little trick. If you have a proportionality statement like this, and you want to make an equality out of it, all you got to do is introduce a constant. And I'm going to call that K. Okay? I'm just introducing some constant, and we'll kind of clean it up. Usually when scientists are playing around and introducing constants, usually they can come back around to what that value of that constant really is. Simply says that, does this make sense? The product, that means you're multiplying. The product of these two needs to be constant. So if P increases, V needs to decrease in order to keep that constant. If P decreases, V needs to increase because you multiply them together and you get a constant. Okay, that's an inverse thing. All right. So I've got some images here to kind of show you. Let's see, pressure and volume. So now to indicate pressure, we've got a few figures that do this. Oops. The gas of interest is right here. And in order for this to make sense, you have to know that this kind of piston thing, that silver thing, can float. That silver thing can float, and it contains the kind of tan gas that's below it. We know the pressure that the gas is forcing in all directions, including the direction of the top of the piston, is related by the mass that's on there, just like a little weight. Okay? So this is to say, if you compare that with this one, what two things are different?
The pressure is less.
The pressure is more because we put a second one on there, and the volume is less. That's right. More pressure, less volume. Oh, it sounds like a beer commercial. Okay? So and it makes sense. And of course, you see a beginning of a graph there with those 2 points. Pressure and volume. Pressure and volume is one goes up, the other goes down. So here's one, if you just have the old-fashioned like tire pump, okay? As you decrease the plunger, you are, move the plunger down. You're decreasing the volume and you're increasing the pressure, and you're counting on that to fill your tire up. Okay. This is one of my. We'll see. I have a series of slides to see what you guys think. This is like a Erlenmeyer flask. You guys have used E-flask, Erlenmeyer flasks, but this actually has a sidearm. It's a thick-walled flask, which means that it can stand pressures, okay, beyond just the old glassware, regular Erlenmeyer flasks. So the gas of interest here in these series of slides, these few slides I'm going to do, actually is contained in this syringe. So can you see where this syringe is about up at the 0? Is that what I want to say? I think so, 0 mark. Okay, so the gas of interest is right here. And notice that the only reason that stopper's there is to go ahead and make it so that gas doesn't go anywhere. The gas of interest is stuck. That's all. All right. So this first slide shows it open to the atmosphere. The next slide, you're actually going to see a stopper up here, too. All right. So notice we went ahead and stoppered it. And what's different about the volume here? Where was the plunger before?
I didn't notice it.
Right, the volume was much higher. This was the old volume. This is the new volume. Yeah, V1 was up there. If you read the caption, what they are doing is basically pressurizing. I'll put increased pressure. They're using a tire pump to basically pressurize that chamber. Okay, and that puts the plunger down. Okay, so increased pressure, decreased volume. I think that's neat. And if you were to compare the previous slide and this slide, now what's the volume? It's even less. So basically somebody has jacked up the pressure. Increase the pressure, decrease the volume of the gas of interest. Now we're dealing with marshmallows. We're back to a neutral state, okay? One of the things about marshmallows, in order for this to make sense, is marshmallows, they taste wonderful, and they are a bunch of sugar and air. Okay, probably not too hard to imagine that. I can't remember what goes first. Oh, yeah. So instead of using the tire pump, okay, we're actually going to draw a vacuum. We have a couple of ways to do that in the lab. I guess the easiest way is just to use a running water and kind of what we call an aspirator. But think of, okay, so if we decrease the pressure, what happens to the volume?
It's gonna get bigger.
It increases. Yep. And so there you go. There's your marshmallows. Okay. So at the lower pressure, the volume increase, the volume that's being trapped by those sweet little morsels. Well, the next one's kind of cruel. So now we change from a vacuum to a tire pump. Okay. So if we increase the pressure, what happens to the volume? Increase pressure, decrease volume. Isn't that adorable? Okay, I just think that is so cool. I'm easily amused. Okay, so I have a few more figures, right? This one actually is the neutral state. I think the next one's in the neutral state too. Now we said that volume and pressure are inversely related. So if we want to get our nice positive slope that we're used to kind of seeing, relationship between two variables like that, if we plot the inverse of the volume, and if we plot the pressure that's being shown here along the x-axis, we should get a straight line. Now I know this says mass, but the reason it's really pressure is we're going to put mass in that open container up there. The gas of interest in these little slides, the gas of interest is right here. Okay? And we're going to put our weights up here. And that mass is actually then represented there along the x-axis. Okay? So it looks something like this. So here it is in its neutral state. The volume in this syringe is 14.3 milliliters. Okay? What if we go ahead and put 500 grams of shot? We're increasing the pressure, and you probably can't tell it in the blink of an eye, but that plunger went down. Now the new volume is 12.5. But notice, with regard to volume, we're not plotting volume, we're plotting the inverse of volume. Why? Because pressure and the inverse of volume are proportional. Yeah. So that's 500. This is 1,000, and this is 1,500. So now you're starting to see, and we do this all the time in science, if you can make a straight line out of any two variables, you've got a connection there. And there's definitely a connection there, as there should be. Okay. Charles' law looks at volume and temperature. A good one, a real practical thing is, like if you buy a balloon and like a Hy-Vee or whatever, but you need it to put it in your car, and your car is really cold, it's a cloudy day out, your car never gets very warm. You go back to your car to then take it in to give it to somebody, and it may have basically looks all deflated, okay? So volume and temperature, yeah. So they're directly proportional. So your temperature went down, your volume went down, okay? That's assuming your pressure and number of moles stayed the same. Okay, so I'm going to replace that proportionality symbol with an equal sign and introduce a constant. But now it's going to look like this. If they are directly proportional, then their ratio will stay the same. So V over T is going to be constant. If volume goes down, temperature needs to go down. If volume goes up, temperature needs to go up. I usually think of monkeying with temperature first, and then the volume follows it, but they go lock and step. All right, the last one, wait, we're going to consider this. So the dark one and the light one, what do you think about the relative concentrations? Which one's more concentrated? The dark one, yeah. Okay. So volume and temperature. Do you buy this then, that at the colder temperature it's going to be more concentrated like this? So let me show you a graph. So we have temperature along the x-axis and volume along the y-axis. Now as one increases, the other increases. As we increase temperature, we increase volume. Okay. The A, B, and C just means 3 different samples of gas. Okay. Now again, we're assuming what's the pressure in both of those? What do you think? How would you compare the pressure in those two?
The ratios are equal.
Yeah, the pressures are equal. The pressures are directly equal. We can tell that because that's a moving piston and we got the same mass on both. What's changing is the temperature. As the temperature changes, the volume changes. I think it kind of really makes sense. I like to think of particles as, I know they are inanimate, but as they cool down, okay, as they cool down, can you almost kind of see them basically kind of huddling together? Okay, the volume will decrease as the temperature decreases. And the volume will increase as the temperature increases. Now, there's something wrong with this plot, okay? The thing that's wrong is the temperature scale. So the only difference between these two graphs is the temperature scale. So instead of Celsius, which is a metric, wonderful metric temperature scale, in order to make sense out of gases, we really do need to switch gears, and our temperature scale needs to be in units of Kelvin. And this actually is one of the reasons why, okay? What happens if we extrapolate, by the way, see these dotted? Anytime you kind of go back or forward outside of your data points, you're extrapolating. Anytime you kind of go within your data points, you're interpolating. I know it's like really extrapolating, extra, interpolating within your data points. So if we extrapolate backwards to colder, 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 colder. What's 0 Kelvin? What's the significance? We talked about this here.
Absolute zero.
Absolute zero, yeah. Absolute zero, all molecular motion stops. Yep. So at absolute zero, what's the volume? Zero. Does it sound like a violation to you? It does to me. One of the things, and we'll talk a little about this in Wednesday's lecture, even more in Chem 2, but the colder you make a gas, the less ideal its behavior. We say its behavior is non-ideal. So it kind of starts to fall apart a little bit. But
Does it also tell you like energy within
yeah.
kinetic energy? The more heat, the more energy, the more volume. Right?
It depends. Yeah, if as long as you're holding, number of moles and pressure the same, that would be. I would go along with that. I would go along with that. So when we start to do gas law problems, and if you have a temperature in your gas law problem, you just have to convert it to Kelvin. I'll go ahead and remind you how that goes in case you forget, because sometimes I forget. If you, what's that?
If it's super cold, will it eventually reach a solid?
Yes, gases will, well, it depends on the pressure. They might go right to a solid, or they might liquefy and then go to a solid. Yeah.
That's sublimation.
Sublimation, I call it deposition, but some people would call it sublimation. Yeah, when it skips the liquid state, it goes straight to a solid. Yep. Very good. So if you have your degrees Celsius temperature, you add, nope, take that back. You subtract, no, you add, oh, are you serious? Final answer. You add 273.15 units, and that will give you your Kelvin temperature. So if you had like -10, yeah, -10 Celsius, add 273, you got 263 Kelvin. Perfect. Okay. So yeah, that's kind of a helpful sort of thing. And obviously then, if you have Kelvin units, you what? Subtract 273.15, and that'll give you degrees Celsius. Now, you might say, well, Mrs. Snipes, you forgot to say degrees Kelvin. And no, I didn't. So the Kelvin units aren't, we don't use the degrees. It's just simply Kelvin units. Cool. All right. So this is a little bit about Charles' law. So the gas of interest, oh, that my video doesn't work. It will later. Oh, I'll go back to this. The gas of interest is right here. And actually, I brought along kind of some things to kind of talk about the 4 parameters of gases and how they relate. Okay, but the gas of interest there, we have it in a water bath. And what this would have shown you is that as we jack up the temperature of the water bath, then your volume increases. That's exactly what it should show you. Okay, so this is a fun one. This actually, I think Dr. Sedlak, does he have liquid nitrogen that he plays around with? Not that you know of, the physics teacher. I think he had talked about it at one time. But this is just a very cold substance. That liquid stuff, you figure nitrogen, this kind of goes back to what Josh was saying. Nitrogen's usually a gas. If you cool it down enough, you can get it to a liquid. So that's really cold. So that's liquid nitrogen. You pour it into a dewar, and we're going to put those balloons in there. So the gas of interest is in the balloons. So as you lower the temperature, what happens to the volume? Yes, okay, exactly. And so that's what you're seeing there. We lower the temperature, we lower the volume. So those cute little moles of gas are still in the balloons, they're just going, okay? But not to fear, okay? The third one says that we're gonna go ahead and take those back out of the liquid nitrogen and they wake back up again. This is kind of like when you buy ants through the mail and they come and they're like cryogenically chilled, and then you guys have never done this, have you?
No.
Okay, so then the ants, when you go ahead and warm them up again, okay. Well, we have a lizard. If you've ever gotten worms by mail, we always get worms for our lizard. They come and they're very cold and they're very slow moving, but when they warm up, they're all wiggly and lizard just loves them. Okay.
Hypothermic state, yeah.
Yeah. So the last one is volume and number of moles, and they are directly proportional. Okay, it makes sense, and that kind of, to me, that's like you're actively blowing up a balloon. Your N is increasing because your gas is increasing, and your volume increases. So if we want to replace the proportionality symbol with an equal sign, we have to introduce another constant. And so then it would look like this, that the ratio of those two, volume over number of moles, will be equal to some constant. So as one goes up, the other needs to go up. As one goes down, the other one will go down. So it remains some constant. Avogadro's law. Okay, can't remember what I had. So this actually is one we'll probably talk again about Friday. So N, the number of moles, is related to volume. N and V are proportional. When we have the stoichiometry of a balanced equation, this says 2 moles react with 1 mole, 2 moles of H2 react with 1 mole of O2 to form 2 moles of H2O. So those are moles. We can also say the same thing about volumes then. We can say 2 volumes, as long as it's like liters, you could say 2 liters, for instance, of H2 would combine with 1 liter of O2 to form 2 liters of H2O. It's wonderful. Basically, we can use the stoichiometric coefficients that are moles and relate them to volumes. It's wonderful. Now, in all of these things where I've taken 2 parameters, okay, that last one I took these 2. That's Avogadro's law, okay? In all of these little scenarios, I am assuming that the other 2 are held constant. So in this case, pressure and temperature were held constant, okay? So that's kind of it throughout. Okay. So let's see, is this where I want to show you a few things? Yeah, before I kind of go on to the next part we got. All right, so we talked about these proportionalities. In fact, we came up with a K, replaced the proportionality symbol with an equal sign, introduce a K. But before we're going to introduce one more K, we're kind of gearing up for the ideal gas law equation. With all of these combined with volumes on the left, okay, we can say that the volumes are all proportional to the things on the right, all put together. So we have what? T and N on top in the numerator and P in the bottom. Okay, directly proportional. So again, we can replace that proportionality symbol with a constant and get an equal sign. So we can say the volume is equal to some constant K times N times T divided by P. Well, and if you're like me, I have to be really careful rearranging things. If I want to get K by itself, and you're in good company if you can't do this. If I want to get K by itself, concentrate, I'm going to multiply both sides by P over NT. Does that make sense? Okay. P over NT. Okay. That's the sort of algebra I'm counting on you being able to do. Okay, so we get PV over NT is constant K. And we are going to replace that K with an R. PV over NT is equal to some constant R. Now this is the ideal gas law
So
constant.
you just showed us the proof.
Yeah, I just showed you the proof of that, exactly. Yep, so R, the pirate's favorite constant. We've got some friends that really like pirates. Okay, well usually we don't see it like this. Usually it's PV is equal to nRT, but it's the same thing, okay? So get your algebra skills on, and I am terrible at teaching math, but I kind of think of that as PV over NT is equal to R over 1, and then this is just how I roll. I kind of think of crisscrossing, okay, and making them equal. I don't know if that must be the way I learned it. So we get PV is equal to nRT. Okay, it's the same thing. Okay, very good. The ideal gas law equation. Dun, dun, dun. So in this universe, R actually has a particular value for linking a gas as long as it's behaving ideally, the N, the T, the P, and the V of the gas. And like I've been saying, it really doesn't care if it's argon, if it's carbon dioxide gas, if it's water vapor. It all kind of rolls with this relationship. So we are definitely all about units. So if you have to work one of these on your, remember your final is going to have 2 sections, multiple choice, and it's going to have the workout. If you have to do a workout section or work one of these problems, you have to include all of your units. Now this is where physics, you might be tempted just to plug in, things and go with it, but you have to plug in things with their units. Okay, so if we go ahead and make, if we make pressure is going to be in atmospheres, that's the one we're going to go with anyway. Volume is going to be in liters. Number of moles, of course, is in moles. T is going to be in Kelvin. Okay, so in order for this to kind of flatten it out and be correct, our R actually will have units of liters atmospheres per mole Kelvin. Liters atmospheres per mole Kelvin. That's the units of our R. And our R will have the value of 0.082058. 0.082058. Units are liters atmospheres per mole Kelvin. And let me just kind of show you how that works. So pressure, I said was in atmospheres. Volume is in liters. N is in moles. I'll put moles over 1. Our R is in atmospheres, liters, ATM, liters per mole Kelvin. I'm kind of running out of room here. And temperature is in Kelvin. I'll put K over 1. If we allow things to cancel, do you see where moles will cancel? Kelvins will cancel. And we actually, in this equality that I have atmospheres liters is equal to atmospheres liters. Okay. It's a wonderful thing. So I do want to get to one problem. I know we're kind of bumping up against we have a minute and a half. So we need to find what we need to know and variables for everything for this. I'll just go ahead, if it's okay with you, and superimpose. If I was working this problem, I would probably draw a picture of my CO2 gas, and I would fill in these blanks as I know. What volume, I would find my V, and I put question mark. And then it would gives me a mass of carbon dioxide. I would find my moles, and I would say 0.20 grams CO2. we can get from grams to moles. Can't we do that? Yes, we can. The pressure is in 732 millimeters of mercury, and temperature is 22.0 degrees Celsius. See, if you do it like this, you're like, oh, okay, I can do that. Okay, so what I would usually do is rearrange carefully, solving for V. I divide both sides by P. That's what I would do. So now V is equal to nRT over P. Kind of set that aside. And the R, the value of R is, I'm going to use that 0.082058 liters atmospheres per mole Kelvin. This slide emphasizes a couple of things. I need to fix my millimeters of mercury. You guys remember when we talked Monday that 1 atmosphere, which is where you need to go, is exactly equal to 760 millimeters of mercury. That's how I'm going to fix this. I got to fix it. The other thing is Kelvin, I got to fix this. And we said we're going to add 273.15 to get to Kelvin. So I got to do those two things on the front end. And I got to fix my mass, my 0.20 grams to moles. So here's fixing my grams to moles. I knock out the molar mass of CO2, 44.01 grams per mole. And then I take the mass, 0.20 times, and that's 0.20 grams, excuse me, times 1 mole over 44.01 grams. So now my N, I know, is 0.0045 moles. Ding, 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 ding. We're on our way. I fix my temperature by taking 22.0 plus 273.15. We don't do a lot of addition, but this is addition. We round according to the nearest 10 decimals. So my temperature is 295.2 Kelvin. We're getting close to getting ready to plug and chug. And last but not least, in this case, not always, but I had to get from millimeters of mercury to atmospheres to use the ideal gas law constant that I want to be using. So I take my 732 millimeters of mercury times 1 atmosphere over 760 millimeters of mercury. So I got 0.963 atmospheres. And if you're doing this on the test, in the last part of the test or for homework, you need to show all of this work. Now I'm ready to substitute in for V. V then is equal to N, which is 0.0045 moles times 0.082058 liters atmospheres per mole Kelvin times 295.2 Kelvin divided by 0.963 atmospheres. Now unit-wise, our moles cancel, our kelvins cancel, atmospheres cancel, and we're left with units of liters, which is great for volume. Rounded to 2 significant figures, I get 0.11 liters. That's it. So I know I'm pushing you, but I do have a couple of problems that we'll be due on Friday. It's only because I care. I've picked 2 of the ones that were in the last slide, yes.
So, R will always be the 0.082058.
Yes. Now, if you look up on the internet values for the ideal gas law constant, there are different values out there, but they have different units.
Okay.
And so you're welcome to kind of, there's one that has it instead of atmospheres, millimeters of mercury, and then we wouldn't have to change.
Okay, so yeah, so
But-
with these units, that's always the number.
Right.
Okay.
So I don't want to throw you off that way. So 27, 28, and 30 will be due on Friday. And the reason I want to get this far, and remember we're going to lecture on gases on Friday, when I go, I'm going to tell you Friday, you might have caught on the slide, I'm not going to go over your Unit 4 exam. I'm going to post the answer key to your Unit 4 exam. okay? I'm gonna give you your graded test back, but you're just gonna be able to see the answer. I might go over it like on my own and push out the video, but I don't wanna take class time. So, I know some of you are anxious to go. I do have hints for these, so you can stick around or go. So these are due Friday. Yes, Rhonda?
The other 6 problems, were those gonna be assigned later?
There will be a sign, yep, when we get to them. But I thought, I kind of like doing it this way because this actually gives you work at PV equals nRT, just kind of the basic PV equals nRT. I've liked doing it this way. So these are these 3 problems, okay? The first one, again, what do? I draw a box. Next to the box, I draw the 4 variables. Don't make them more complicated than they are. So you can see from my kind of scribblings there that it's very similar, it looks like, to this one, where you're not given N, but you're given grams, right? You can use, yeah. So it's very similar to this one. The next one, I think I like drawing a box and putting that outside because I just kind of like stalling, right? So just reading my notes, you can see that you're given the volume. Again, you have to get moles from grams. You have to convert Celsius to Kelvin, and you're after P. You can do that, okay? I don't know if you can do it in your sleep necessarily. But these 3 are pretty straightforward. And then actually on Friday and then next week, we're going to kind of take some kind of, I won't say twists and turns, but look at the ideal gas law and kind of take some different sort of problems. Okay, this one you're after T. I'll push these out there. Okay, any questions? Yep. All right, thanks for your patience.